Welcome to G Fun Facts Online. Today we are not talking about the shiny high-speed electric cars that grab all the headlines. We are talking about the invisible backbone that makes them possible. We are talking about the grid, and specifically, why the energy transition is currently hitting a wall. For over a decade, we have been sprinting toward a renewable future. We have scaled wind and solar from gigawatts to terawatts. But this transition relies on a foundation that is starting to crack: lithium-ion batteries. We are facing a paradox. To decarbonize the world, we need to store massive amounts of energy. Currently, we do that by packing highly reactive, flammable organic solvents and scarce metals into dense cells. We are effectively stacking chemical fire hazards next to our most critical infrastructure. Supply chain volatility, geopolitical bottlenecks, and the sheer cost of raw materials are threatening to stall everything. But there is a solution emerging from the labs, and it is not just a tweak to existing chemistry, it is a fundamental reimagining of how energy is stored. It involves taking one of the most abundant elements on Earth, sodium, and combining it with the most abundant solvent, water. This is the story of hydrosodium dynamics and the rise of aqueous sodium-ion batteries. To understand why this is such a massive leap, we have to look at the limitations of what we use today. Lithium-ion batteries are, without a doubt, a miracle of engineering. They gave us the mobile revolution, but they rely on organic electrolytes. These are solvents derived from petrochemicals, and they are necessary because lithium reacts violently with water. The problem is that these organic solvents are flammable. If a single cell fails, it can trigger thermal runaway, a self-sustaining fire that is incredibly difficult to extinguish. For a grid operator, that is a nightmare scenario. On top of that, we have the supply chain: lithium, cobalt, nickel. These are expensive and concentrated in very specific parts of the world. Now imagine a battery where the electrolyte is just water. This is the promise of hydrosodium. Water doesn't burn. You could drive a nail through an aqueous battery, or even shoot it, and it will not catch fire. Sodium is over 1,000 times more abundant than lithium. We can harvest it from soda ash mines in Wyoming, or desalinate it from seawater. The materials are everywhere. But historically, aqueous batteries were a dead end. This brings us to the core science and the problem known as the water window. In any battery, ions move between a cathode and an anode through an electrolyte. If the voltage difference is too high, the electrolyte breaks down. Pure water splits into hydrogen and oxygen at just 1.23 volts. That is a pitifully low voltage. A standard lithium cell operates at 3.7 volts. Since energy equals voltage times capacity, a water-based battery usually has terrible energy density. This is where the breakthrough happened. Scientists developed something called water-in-salt electrolytes. Imagine a glass of salty water. That is salt in water. Lots of water molecules surrounding a few salt ions. But if you dissolve a massive amount of specialized salt into a tiny amount of water, the physics flips. You get a super concentrated state where every single water molecule is recruited to form a solvation shell around a sodium ion. There are no free water molecules left floating around. Because the water molecules are so tightly bound to the sodium, they become chemically stabilized. They resist splitting apart. This expands that voltage window from 1.23 volts to nearly 3.0 volts. Suddenly, water-based batteries can compete with lead acid and even some lithium chemistries, but with zero fire risk. This concentration also suppresses something called the gratis mechanism. In dilute water, protons hop rapidly between water molecules, causing self-discharge. In this thick, viscous water and salt electrolyte, that hopping is physically blocked. The sodium ions dominate the transport, meaning the battery holds its charge until you need it. But the electrolyte is only half the battle. You need electrodes that can survive in water. Enter the superstar material of this technology: Prussian Blue. Yes, the same pigment used in blueprints and famous artwork, like the Great Wave off Kanagawa. At the atomic level, Prussian Blue has an open cage-like lattice structure. It has massive doorways that allow sodium ions to swim in and out with almost zero friction. This leads to a property called zero-strain insertion. Lithium electrodes physically expand and contract when they charge and discharge. They breathe. Over time, that breathing causes cracks, which is why your phone battery dies after a few years. Prussian Blue doesn't do that. The sodium enters without deforming the structure. While a lithium battery might last 2,000 cycles, a Prussian Blue sodium battery can hit 50,000 cycles. That is decades of daily use with almost no degradation. On the anode side, we are seeing materials like sodium titanium phosphate, or NTP. These are stable in water and allow for rapid charging. We have even figured out how to form a solid electrolyte interface, or SEI, in water. This is a protective layer that forms on the anode, something scientists thought was impossible in aqueous systems for decades. Now, let's talk about money, because the best science in the world doesn't matter if it's too expensive. The economic argument for hydrosodium is devastatingly strong. First, the raw materials. Lithium carbonate prices fluctuate wildly, sometimes hitting $70,000 per ton. Sodium carbonate costs roughly $150 to $300 per ton. It is dirt cheap, but the real cost savings come in manufacturing. Sodium-ion is a drop-in technology. You don't need to build new factories from scratch. You can use the same roll-to-roll coating machines used for lithium batteries. However, because the electrolyte is water, you don't need dry rooms. Lithium batteries must be assembled in ultra-low humidity environments because moisture destroys them. These dry rooms are incredibly expensive to build and run. Aqueous batteries don't need them. Eliminating dry rooms can cut the capital expenditure of a gigafactory by 20 to 30%. When grid operators look at batteries, they don't just care about the upfront price tag, they care about the levelized cost of storage. This includes the lifespan, safety, and insurance. Lithium has a moderate lifespan and high safety costs due to fire suppression systems. Aqueous sodium has a moderate upfront cost that is dropping fast, an extreme lifespan of 20+ years, and zero fire safety costs. Over the life of a project, it is significantly cheaper than the current standard. This isn't science fiction. It is happening right now. Companies like Natron Energy are already in commercial production. They opened a massive facility in Michigan in 2024. Their batteries aren't for cars. They are for high-power stationary applications like data centers. Data centers need massive bursts of power to bridge the gap between a grid outage and their backup generators kicking in. Natron's batteries can discharge their entire capacity in minutes safely. Try doing that with a lithium battery, and you will melt the system. Then there is peak energy, deploying grid-scale systems that require no active cooling. Lithium systems need chillers, pumps, and radiators to keep the cells at the perfect temperature. Aqueous sodium batteries have a high thermal mass and no risk of thermal runaway, so they can often be air-cooled. That removes huge maintenance headaches. Of course, we have to address the elephant in the room: energy density. You cannot pack as much energy into a kilogram of water and sodium as you can into organic solvents and lithium. Hydrosodium batteries are heavy. You will probably never see one in a Tesla Model S. But here is the thing. For the grid, weight is irrelevant. A grid battery sits on a concrete pad. It doesn't need to move. The primary concerns are cost, safety, and longevity. In that arena, hydrosodium wins hands down. It is also the ethical choice. We aren't depleting water tables in deserts for lithium or dealing with human rights issues in cobalt mining. The materials are iron, manganese, aluminum, and soda ash. Recycling is trivial because there are no toxic solvents to neutralize. The black mass is non-hazardous. Looking ahead to 2026 and beyond, we are moving from validation to utility adoption. We expect to see these batteries replacing gas-fired peaker plants. Research is pushing the voltage window even higher, with hybrid electrolytes and anode-free designs that could double the energy density. We are witnessing the blue revolution. The narrative of the energy transition has been dominated by the search for more density, batteries that let us drive 500 miles. We achieved that. But the grid needs stability. It needs a technology that can be deployed at the scale of terawatts without consuming the world's supply of rare earth metals or creating a global fire hazard. Hydrosodium dynamics is the maturation of battery technology. It is the shift from exotic performance to pragmatic utility. The lithium age was necessary to start the revolution. The sodium age is necessary to finish it.